We will wait for 2 to 3 minutes, then let other people to join. Then we will start. Okay. Okay, so let us start. I think if people are joining, then I will let them in. So it's already 6:09, so we can start. And also the session is being recorded, so it will be not a problem. Those who are missing, so they can look into it later on as well in the YouTube, but the discussion will not be there because here if you are present then one to one discussion is possible, but in YouTube that can be possible. So yeah, so with that I welcome you myself, Saumyadeep Goswami. Good evening everyone. Today we are going into the week 7 contents. Mostly not into the week 7 contents because last class also I talked about NMR. So what I have finished is that we have discussed about the extracrystallography part, and we have started little bit about NMR in the last class. So because I am means I have also discussed X-ray crystallography in the last class, so the NMR part was not yet over. So I would like to finish the NMR in details, and then actually we will start with the spectroscopy content if we have time today. So that is the week 7 content. If you see in sir's means slides which is present in your week 7, so it is mostly about the different spectroscopy techniques. So before going into the spectroscopy techniques, I will like to give you some means we will like I will like to discuss about the NMR technique little bit, because that is also very important. So before starting, if you have any question you can ask me, and anything if you want to ask, uh, any questions about the previous contents. And also I will actually solve the week 6 assignment today, means thus I will give you the solutions of week 6 assignment. So yes, if you have questions with week 6 assignment, then you stay tuned. You will get the answers in the end of today's discussion. But other than that, if you have any doubt regarding what I have discussed, and till week 6 content, anything if you want to discuss, I will be happy to do so. Okay, so if you don't have any doubt, then it's fine. You can actually write to me, and also if you have any doubt, you can join in the next sessions as well. So I will be always here in 6 to 8 in each and every Friday. So you can come and you can discuss. Okay. So, since in the last class we talked about NMR, so just a brief that we talked about in the last class, so that you were not in that position that you are starting in between. So I am giving you a gist that we have talked about in last class. We said that from the name itself, nuclear magnetic resonance. So here in exocrystallography, we were more concerned about the electrons, which are responsible for the diffraction, X-ray diffractions, which we get in exocrystallography. But in NMR, we are more concerned about the nuclei of an atom, which consist of the neutron and the proton. And I said you that all the nuclei are not NMR active, and there are certain specific nuclei which has a non-zero spin of their protons and neutrons, and that is possible in most cases when they have either even atomic number, or an even mass number, or both the mass number and atomic number is even. If these are the conditions, then means if they are not so sorry if they are not even, then it's the case that they are NMR active, means there should be an always net spin of the nuclei, means the mass number or atomic number or both, if they are odd, not even, then they are NMR active nuclei. Okay, so that is written in this slide, and I have discussed with you that what is the spin quantum number, and how what are the different states of the spin quantum number. You can find out with this 2i plus 1 means this can give you the number of allowed spin states, and what are the different nuclei which are NMR active. Like the carbon 12 is not NMR active because of this even means protons and neutrons which cancel out their spins, and the net spin of the carbon 12 nuclei is 0. So this is not NMR active, rather than 13 C or the carbon 13 is NMR active, proton is NMR active. Okay, so and nitrogen 14 is NMR inactive, in nitrogen 15 is NMR active. So, what I missed here, let us go through it. I will also, what I didn't discuss last week is that as you should ask a question always that the samples that we work with in our lab, if it is a biological sample, then they are made up of carbon 12 and nitrogen 14 only. So how then we can actually form the structure of our proteins which are made up of carbon 12 as well as nitrogen 14, because they are NMR inactive. They can't be used to visualize your structure in the NMR. So that for that what we do is that there is a protocol that we need to follow. So I will discuss little bit. First let me give you the summary of what we discussed last week. So I said you that this nuclei which has a dielectric constant and they form a dipole, so this can be in different directions, but once you apply an external magnetic field, they will be either antiparallel or parallel to the external magnetic field, because we know that if a magnetic field is produced around it, an electric field also get produced, due to which your dielectrics, which are these nuclei, they will either align in the positive uh, in the parallel or anti-parallel direction with respect to your applied magnetic field. Okay, so then we said that there are two spin states, because on the direction of which these nuclei align, that is the negative half state and the positive half state for the proton. Okay, so I am talking mostly about the proton here. So where you find out that since the proton has a spin half value, this I value is half, so number of allowed spin states for proton is 2, that is plus half and minus half. So then we talked about that there is a net difference between this plus half and the minus half. That is this, there is a small population difference between this minus half and plus half state, due to which this uh, NMR occurs. What happens is that since this plus half state is your ground state and this minus half state is your excited state, and between these two states there is a energy gap, which if you provide an external energy similar to this energy gap, then the protons which are present in this ground state, the extra protons which are present in this ground half plus half ground state, they will get excited to the minus half state, and after some time, they since they are in the excited state, they will again try to come back to their ground state. Okay, so this del E energy, if you apply a similar energy for different nuclei, this is for proton, and for for nitrogen this energy difference will be different. For carbon this energy difference will be different. So if you need to, that's why it is nuclear magnetic resonance. So you apply a magnetic field in such a way that it is actually helping to cover your this energy gap, due to which this transition occurs, and during the emission there is a free induction decay that we talked about here. Is that so? First what happens is that because there are in the x and y direction, this all means spins that you see, they have a moment, right, on the in the magnetic field, and this moment will be cancelling out in the x and y direction, because these moments in the x and y directions are equal. Since you have applied the magnetic field in the z direction and there is a population difference in the z direction, that is there is a little bit more amount of plus of nuclei in the ground state, due to which you will have a magnetic moment which is aligning to your z direction, that is parallel to your external magnetic field. This magnetic field is kept on for always. If this magnetic field is not present, then you cannot perform the NMR, due to which this magnetic field, by this name of the magnetic field, NMRs are defined like 600 megahertz magnet. 1 minute. Okay. Okay. So yeah, so what I was discussing, the basics of NMR here is that we need an external magnetic field which is essential for your means magnetic moment, to be in the direction of the z direction, and in the x and y direction this magnetic moment cancel out each other. But since in the z direction there is a population difference between this lower energy state and the upper energy state, so you have a net magnetic moment in the z direction. But then what we do is that we apply a radio frequency pulse which will create a magnetic field. Since it's a radio frequency pulse and you know it's a coil. Okay, so through a coil if you pass electric current, it will produce a magnetic field, and that magnetic field will be perpendicular to the external magnetic field, due to which, if you now you imagine that a magnetic field is produced in this x direction, okay, due to this 90-degree RF pulse. Okay, so the in NMR you will see that there are different kinds of experiments of NMR that you can do by varying this pulse and this delay time. Okay, so these two entities in NMR is very important, on the basis of which many experiments in NMR has been designed. Okay, so once you apply a magnetic field in this x direction, so that will create an electric field in perpendicular to it and will help this magnetic moment which was previously aligning to this z direction to come to this y direction. Okay, because there is a magnetic field that there is an electric field that has been produced here. So your magnetic field is in this direction, that is your B. Okay, and that is perpendicular to this external magnetic field. And since it is producing magnetic field in x direction, there will be a electric field in this direction perpendicular to the magnetic field, due to which this z moment will now fall in the in this y axis. Now, this y-axis, because there is always this 90-degree pulse is given for a period of time, then it is removed. After removal of this 90-degree pulse, this there is still this magnetic external magnetic field that is on, due to which there will be a magnetic electric field in this direction, right, perpendicular to, if you curl your finger by keeping the thumb to this magnetic field, external magnetic field, you know that it will be in the perpendicular direction, due to which this magnetic moment which get fold into this y axis, it starts precessing around this xy plane. Now you give a delay time to which it will precess and it will come back to its original position. Why that is so? And in that path, because this is precessing, and in that path, what will happen is that this, since any magnetic moment which is revolving around a electric field, it will lose some kind amount of energy to come back to this original state, and that energy, that loss of energy, is being detected by two detector present in this x direction and y direction. That is your free induction decay in the x direction and the y direction. Now in the free induction decay, this free induction decay you can't visualize for each and every atom, because these are some sine waves. You require these sine waves to compile, or say, to make it compile to one another, you do a Fourier transform, so that these sine waves or this free induction decay, now you can visualize it in terms of frequency. Free induction decay was in terms of this time. Now after doing Fourier transform, you can see this free induction decays in the form of certain distinct peaks. Now this will be easily visualized, and this can actually give you information about the structure of your protein. So this is the overall procedure of the NMR. Now you can vary this 90-degree pulse and also means the pulse sequence and this delay time, so that you can create different NMR experiments. Okay, and the frequency by which this magnetic moment precess in this XY plane, that is your precision frequency or Larmor frequency, and this Larmor frequency is equal to this E equal to h nu, that is in between there is this energy gap that I talked about, between these two states, that can be written as h nu by Planck's equation, Max Planck's equation, and where nu is your frequency, this frequency is this Larmor frequency with which this magnetic moment will precess in this xy direction. Okay, and ultimately you will get peaks like this. So this is the theory behind how you get this NMR spectra. Okay, then I said you that if that is the case, you will get always a frequency spectra with respect to the protons, and there will be no difference if you have a structure like CH3, then means CH3, CH2, and then other means, for example, you have a propane, and in propane, all the hydrogens, if this is the simple as this case that I talked about, then all the hydrogens should have given you a single peak. And if that was so, then you couldn't have drawn this information to find out the structure of the propane. Okay, you can find out that the structures of propane because these protons are not similar in a chemical structure. What is very interesting in NMR is that you can actually see the effect of your chemical environment on your structure. That's why you can actually visualize the dynamics associated with your proteins or with your sample in a particular chemical environment that cannot be visualized in other techniques like X-ray crystallography. So you can see the dynamics. Why that is so? Because your nuclei is surrounded by a electron density, means they are surrounded by electrons, right? So these electrons, since they are revolving in circular motions around these nuclei, they will also create an electric field. That electric field will hamper, or that will not allow the net electric field generated by this external magnetic field to impact the nuclei equally. Means those which have a lesser electric field, means or lesser crowding of the electrons, those nuclei which have a lesser crowding of electrons around them, they will be experiencing a different electric field or different shift. And in those nuclei which have a lesser crowding, or they will actually see another chemical shift. This from here you actually come to the concept of chemical shift. Means there is a shift, the proton where it should come, due to that chemical environment change of this proton, you are not getting the proton shift in that region, or rather you are getting that peak in a region which is shifted. So that's why this is written as this due to this chemical environment there is a shift. So you got a chemical shift. 1 minute. uh, Someone is trying to join. Okay, so yeah, so we were talking about the uh, shielding of the protons in the chemical shift due to which you get a signal, okay, in NMR. So that concept can be actually visualized with the help of this example. So here if you see that all of these are protons and all of these are NMR active. But what has happened here is that this proton which is attached to this oxygen, this proton and all these three methyl protons, they are not the same protons because they are facing a different chemical environment. Because this hydrogen, this proton is attached to this oxygen, and as you know, these oxygens are more electronegative, which means they are more electron loving. So this oxygen, what it will do is that it will drive these electrons which were present around this proton towards it, due to which you will not see this shielding effect for this kind of protons which are attached to this oxygen, and it will be less shielded. It will be less shielded, this proton. But since these three protons are not attached to an electronegative group like this oxygen, So due to which these three protons will be more shielded as respect to this proton which is attached to this electronegative element. So when you will do a proton spectra for this molecule, you will actually get two different peaks. Means one peak which will correspond to this proton, another peak which will correspond to these three protons. Okay, and for reference, now whenever you are actually doing one experiment, it is important to measure something to have one reference. Okay, so for reference, normally people use this tetramethylsilane. So tetramethylsilane. So there is a silica group and there are four methyl groups attached. Okay, tetramethylsilane. And because of this, there are four methyl groups. So these the protons which are present, they are experiencing a higher shielding or most higher shielding of these protons, methyl protons will experience, due to which we sometimes use this TMS as our zero chemical shift. Means it is the most shielded. The more you come towards zero in a chemical shift, it means that it is more, the proton is more shielded. The more you go away from your zero, the zero delta value zero, it is a more deshielded. Okay, so if you imagine this proton which is attached to this oxygen, that will be coming towards this region more downfield. Means the chemical shift value will be more for this proton. Okay, because it will experience more electric field, you would say, or the magnetic field effect on this less shielded proton will be more as respect to these three, because they are more shielded and their electrons are actually creating an electric field which will hamper the effect of this external magnetic field, due to which you will get a less shift, or you will get a less chemical shift for these shielded protons. Okay, so and this chemical shift values is can be determined by this shift in hertz, the shift in hertz divided by the spectrophotometer frequency in megahertz. There is a spectrophotometer frequency that I said, like 600 megahertz, 800 megahertz. So the more the magnetic field, more higher the resolution. Okay, so normally for proteins we require 600 megahertz magnets. Okay, then, as I said, that these protons, on the basis of their different chemical environment, they will show different chemical shift values. So, for aldehyde and this carboxylic acid, since there is a resonance of these electrons here, okay, so due to which the electrons which are present in this proton, they are drive more towards this group, carbonyl group, okay, and this proton is most deshielded, due to which you get a higher chemical shift value for the carboxylic acid, as and also there is this aldehyde, because here there is a resonance, due to which you get a higher chemical shift value than this aldehyde group or this carbonyl group. Okay, and as you go more towards zero, you will find this alkane like methane, methane, propane. Okay, so all these will have these protons which are more shielded because they are not attached to any electronegative group. Okay, so this I gave you the table last class. Then I discussed that what are the different things that one can actually visualize from these NMR signals. If I said you that the number of signals shows how many different kinds of protons are present. As I mentioned that this molecule that we discussed, for this we will get at least two kinds of peaks we can actually see in the 1D proton spectra. Then there is this concept of splitting which will not happen here because there is no subsequent carbon. Okay, so what is splitting, I will be coming. Okay, so the number of signals will tell you that how many different kinds of protons are present. the location of the signals will show you whether they are more shielded or de-shielded. Okay, so means if the way I mentioned that if they are more near to the zero, then they are more shielded, and if they are away from the zero, means they have a higher chemical shield value because they do not have their electron cloud is not affecting the protons to experience the external magnetic field. That's why they will have a greater chemical shift. So they will be more de-shielded. Okay, and the intensity will show you that how many protons are behaving in a similar way. Means if there are three protons, you will get a higher peak as compared to the protons which there where you have a single proton. Okay, which is actually giving you the intensity. The intensity will tell you that how many protons are facing the similar chemical environment. Then there is the splitting. The splitting actually helps you to tell that what is present, means there is this proton, the CH3. So what is present means how these protons is affecting the protons which are present in another subsequent group which is attached to this carbon. Means it actually, the splitting actually give you the information about the protons present in the adjacent atoms. Okay, so all this information are very important to solve the structure of us from a small molecule to a protein. So we will be seeing some example today. So all this that I have talked about, these all I have discussed last class, but last class many of you were not present. So I thought that to start from for starting today's session, let me give you a summary. So I have given you that summary that I discussed last class. So now we are actually going into the splitting. Okay. So we know that from the chemical shift, the location, we know that how much it is deshielded or not. The intensity will give me the number of protons. But what will those information serve if I don't know that what is present in my adjacent? Because once you don't know what is present in your adjacent carbon or how the protons are behaving in your adjacent atom, how can you actually draw the structure? Okay, so this information is very important. So that is given by the splitting. Means that if there means the protons for proton spectra, means you will follow this splitting n plus 1 rule for both proton as well as carbon spectra. But for proton spectra, you remember that these protons can actually see the protons which are present in its adjacent carbon if they are 3 bond distance apart. Means if I will show you, means so if you have one carbon which has one proton attached here, okay, and there is a subsequent carbon which also have one proton attached here. So it has only single proton, then there are two protons which are present here. Now for these two protons, since these two protons are facing a similar chemical environment, you would have expected that they should have given only a single peak in the NMR spectra. But that is not the case because this proton J coupling value, this is known as the coupling value, means these protons chemical environment can be affected by these protons chemical environment because they are separated by a 3 bond distance 1, 2, and 3. So this proton can actually affect the environment of this proton present in its subsequent carbon, adjacent carbon, because this J, because of this splitting constant or the coupling constant that is given by this J. And this J coupling constant for protons means one proton can actually affect another proton only if they are in a distance by 3 bonds. Okay, so that is the coupling constant through the bonds. Okay, it is written as JHH. Okay, the coupling constant between two protons, and this is non-zero, due to which you will see that in this spectra you will not get a single peak. Rather, this proton will actually split this the peak which should have arisen due from this proton, this one proton. So how it will split, means in what ratios it will split, that is given by this n plus 1 rule. So if you are looking for this for the proton attached to this carbon, you should look into the carbons or the means or the hydrogen or the protons which are separated by 3 bond distance in the adjacent carbon. So if there was something here, you would have counted the protons in this direction as well. So the basic idea is that for finding the splitting means of a peak of a particular proton, you should look into your adjacent carbons. I am telling this for 1H NMR spectra. So this is for proton spectra. If you are taking a proton spectra, then apply this. There is a shortcut. What I am telling you is that if you want to find the splitting of this proton, you look into the carbon atoms which are adjacent to this carbon and try to count that how many protons are present. So if there is a one proton present here, here there are two protons, for example. Okay, means in this carbon. So then the protons, the peak that you should got for these two protons, you want to calculate the splitting of this proton, that will be you add this the adjacent carbon protons, that is 2 plus this one. Okay, so 2 plus 1, that is 3, and add 1, that is n plus 1 rule. You need to look into the number of protons attached to the adjacent carbon atoms, count them, and then add by 1. So for this carbon, the protons that you have, you this one peak will be splitted into 4 different peaks. And the how it will be splitting means what will be the intensity, that will be given by this Pascal triangle. So this is a quadrate because this chemical shift is splitted into 4 different shifts because of the protons present in its adjacent carbons, because of this JHH splitting. Okay, this scalars coupling splitting, due to which you will get a quadrate. And what will be the intensity difference? That can be given by this. See, there will be a small peak. 1 means small peak. Then there will be a 3, means three times the, if you see the peak height of this compared to this will be 3 times. Then again there will be another 3, because the 1 3 3 1. Then there is this. So this peak will be actually coming in your NMR spectra like this, like this. Okay, and the difference between these two peaks, these two in the difference between the peaks which are being splitted. Okay, this is a single peak which got splitted into this 4. The difference between them is equal to this JHH value. Okay, so this is the idea of splitting. Now let us take the example of this molecule CH3 CH2 Br. So you practicing for starting your practice, you can take a chemical molecule or small molecule, and try to visualize that how will its NMR spectra look like if I take a 1D means one dimensional proton spectra. Okay, so then how it will look like? You will find that this, since now you can actually count with me how it is happening. So first we will be looking for the protons of this methyl carbon, because in this methyl carbon all these 3 protons are present in a similar chemical environment. For all these 3 protons you will get only a single peak. You should have got only a single peak, because all 3 protons are in the similar chemical environment. So this is CHHH. Okay, they are not facing different chemical environment. So ideally you should have got a single peak, means what I said, that you should have got two peaks, because this proton is facing, these two protons are facing a similar chemical environment. These three protons you should is facing a similar chemical environment. Ideally, for this molecule, you should have got two peaks, one for this proton, another one for this green color proton. But that is not the case because of the splitting. There is this hydrogen, this blue hydrogen is connected to this green hydrogen by three bonds. So for this, the peak of this blue hydrogen will be splitted by the green hydrogens. Okay, so how, in what ratio they will split, how to count it? I have said you that look for the protons, number of protons in the adjacent carbon. So when you are actually looking for this blue hydrogen spectra, you should count the number of protons of this green. So there are two protons. Now you apply this n plus 1 rule. So n is 2 here. 2 plus 1, that is 3. Okay. So you can see that for this blue protons, that is this one, which you should have got a single peak, that is being splitted into three different peaks. And the difference between these two peaks is the J coupling constant value, that is this JHH. JHH. Okay. Now, how this splitting is happening? Can anyone explain me? Can anyone of you two, means how for this green color proton, it is being, you can see four peaks here. Why that is so? Can anyone explain me? Any one of you? You are getting the idea, right? Means whatever I explained you, because this is very important. If you don't understand, just tell me. I will. What? Repeat. Mhm. Hmm. Yeah, exactly. So that's why this you get this splitting, right? Means I explained here that why you get this splitting, that this hydrogen, means you consider this example. So these three protons which are attached, these blue protons, they are in a similar chemical environment, right? So you should have got ideally a single peak in the NMR spectra for these three protons. You shouldn't have got all these three different peaks, because I said that on the basis of the chemical environment you will get the shift. These three blue protons are facing the same chemical environment, so you should have got only a single peak. But why you are getting three different peaks? That is because you said correctly that this proton, this blue proton, this, if you if you means visualize like this, there are three protons attached like this. So there is one proton here, so there is one proton here. So I am writing this CH3 in this form. Okay. And there are two protons which are present in its adjacent carbon. Okay. So I am writing this means this chemical formula in this branched form, so that you it will be easy for you to understand. Now, what I said, that they are, due to these three protons, they are facing a similar chemical environment. So for these three protons, you should have only a single peak, but you see three different peaks, because this is because you see there is this carbon-carbon bond in between these two carbon. If you see this proton, one, two, three. So three bond distance is there. So I said that if a proton is separated by another proton in three bond distance, then that proton can actually split the peak of the proton that you are looking into. Means, since this green color protons, for example, green color protons, they are in three bond distance from these blue color protons, the chemical environment of this proton can be affected by these green protons, due to which you actually see a splitting of these blue protons. Okay. So in what, how many peaks it will be splitted? that is given by your n plus 1 rule. What is n plus 1 rule? Means for if you want to calculate the splitting for the blue protons, you look for the protons which are attached to the subsequent carbon, that is here these green protons. You count them. That is your n value. Means for this blue color proton, the subsequent carbon has two protons. So the n value for this proton is 2, and 2 plus 1. So 3. That's why you get 3 different splitting for the blue proton. Okay. Now I am asking you that can you explain why for this green proton you see 4 different splits? Means 4 different peaks are coming. Why that is so? Just the way I explained you the blue one, can you explain this green peak to me? How you are getting these 4 peaks? No, no, we are not considering bromine because bromine does not have any proton. We are actually considering the protons because, yeah, mhm, yeah, for which one? Yeah, yeah, in the green one, right? Why it is 3? N is equals to 3. Why it is n equals to 3? Yes. Mm-hmm. Yeah. Oh, no, no. You are counting the bond. No, no, but you don't count the bond. Okay. I am telling you what I said about the counting the bond is just why you are actually why these blue protons are affecting the green protons. Only they will be affecting each other when they are in a 3 bond distance. Okay, that doesn't have anything with the n. Okay, so once this criteria is satisfied by that this proton is actually in a 3 bond distance with this proton, then you need to calculate the n by looking into the number of protons which is present in the adjacent carbon. Means when you are calculating the splitting for this proton, you need to see what is the adjacent carbon here. Means this is the carbon, and which this carbon is attached to which carbon? This one. So how many protons are present in this carbon? There are 3 protons, right? So that is your n value. Then you are adding 1, that is 3 plus 1. That's why you are getting this green proton is splitted into 4 peaks because its adjacent carbon, means the proton in which it is carbon is attached, this carbon's adjacent carbon has 3 protons. And you follow this n plus 1, here n is 3 because it has 3 protons. That's why 3 plus 1 you get 4. That is why you have 4 different peaks. It's clear? Yeah, because yes, because in the subsequent carbon, this means green color carbon is attached to this blue color carbon, right? Now this blue color carbon has 3 protons. So this n value for this green color carbon is 3 because the blue color carbon has 3 protons. You understand? Due to which you get n plus, then you add n plus 1, that is 3 plus 1 is 4. Now if you calculate for this blue color proton, you need to see the number of protons where, what will be the n value for this blue color protons? Yes, so what will be the number of protons, n value for this blue color? 2. Good. So that's why is 3. Yes, that is triplet. So that's why you are getting here this 3. Okay, for the blue one, count 1, 2, 3. Okay, now you can actually know means how this splitting occurs. Okay, I think you are clear, right? Okay, so now you can ask that, sir, why this green color peak? is more towards, means is has a higher chemical shift than this blue colored shift. Blue colored blue colored peaks. Why it has a lesser ppm value than the green color peak, or opposite, means green color peaks have a higher ppm value than these blue color peaks. Why that is so? Can you answer me? I have given this answer while explaining. Yeah, good. Why this blue color is means this blue color is more shielded, or green color is more shielded? Blue color is more shielded. Why green color is less shielded? No, no. I am telling you. You are telling that blue color is more shielded because it is away from bromine, right? What you are telling? Can you explain? You said correctly that blue color one is more shielded. More shielded means that the electrons are intact with it, right? There is no electronegative group attached to it. So that's why your blue color one is more shielded, right? But this green color peaks, why it is coming in this higher ppm, means these are less shielded. Why that is so? Because these green color protons, they are in a vicinity of an electronegative element, that is bromine, due to which the net electron cloud shifts towards this bromine, due to which you get a lesser shielding, due to which you get a higher ppm value for these green color protons. But these blue color protons, since they are far from this bromine, that's why these protons are more shielded as compared to the protons which are in the vicinity of this electronegative element. It's clear, right? Okay. Nice, good. So thank you for practicing with me, because this will actually clear your doubt, and this is all why I am here. I should clear your doubts, and this kind of spectra can come in your exams as well. Okay, so that is about the proton NMR. So now I think you are clear about the proton NMR. Here we are doing the proton NMR, means we are applying a this del E value, or this Fourier this Larmor frequency that I was telling. So this del E value, that was respect to your proton. So that's why we are getting this proton spectra. Now, if we are applying this del E value or the radio frequency in such a way that it matches the energy gap between the carbon 13 nuclei. Okay, if that is the case, then you will get a carbon spectra. What we got here is a proton spectra, means how these protons are behaving in that electric field, because we gave a pulse whose frequency is matching with the proton frequency. Now if you change the radio frequency in such a way that you know for carbon 13 what is that energy gap value, that is what resonance is happening, nuclear magnetic resonance. So you change the frequency, you get another spectra, that is a carbon spectra. Now, instead of getting for these protons the peaks, you will get the shifts for your carbon. Okay. Now you see that for this carbon, if you want to see this n plus 1 rule that you just applied for the proton spectra, that will not be directly applying to your carbon spectra. Why that is so, I am telling you. I said you that in the proton spectra, so you just try to understand. This is sometimes difficult to understand. If you find any difficulty, stop me and tell me. But this concept should be clear. Okay. If you see this molecule, so I am actually uh, drawing this ethane. Okay. So you have these three protons attached to it, and you have these three protons attached to it. Now, if I tell you that collect me a proton spectra, then for this proton, I said you that you should see by 3 bond whether there is any proton in its vicinity or not. So 1, 2, 3. Okay, so you found some protons. Means these protons will affect the chemical environment of this proton. That's how you were calculating this by n plus 1 value, because your I said that this J coupling means J coupling between this proton that can actually see to 3 bond distance. Means this J coupling value between protons is in between 3 bond distance. That's why this proton can affect the chemical environment of this proton, due to which if you take a proton spectra for this proton, you will get how many peaks? How many peaks? For if you take a proton spectra of this proton, how many peaks you should get by splitting? Good. So you should get four protons, four splits, because in the subsequent carbon there are three protons, and this proton and this all three protons are connected by 3 bond distance. So you should get four shifts. Now, if I tell you that okay, I am not doing a proton spectra, instead I am doing a carbon spectra. Now let me tell you that this J coupling value between carbon to carbon is nearly zero, because this carbon 13, the 13th the carbon 13, this carbon 13 abundance is very less in nature. This is around 1.1%, and other 99.9% of the carbon that we find is carbon 12. So the probability that you will get two carbon 13 atoms subsequent with one another, that is very difficult to get, because you have very less abundance of this carbon 13. And I said you that carbon 12 is not NMR active. So you should have carbon 13, then only you will have this NMR active samples. But since this carbon 13 has a very lower abundance, that is 1.1% only, so the J coupling value between two carbons is nearly zero. Means this carbon will not be affected by this carbon. Okay, for protons it was being affected, because this J coupling between the protons was in a 3 bond distance. You if you have any proton, that proton can affect the chemical environment. But the J coupling value between two carbons, since I said this due to this abundancy issue, the coupling constant between two carbon is near to zero. Means this carbon will not affect the chemical environment of this carbon. So it is clear, this carbon will not affect the chemical environment of this carbon. But you have protons, right, attached to this carbon. Now what will happen is that if you take a proton as well as a carbon spectra, and this carbon this coupling constant between this carbon and proton is not equal to 0, this is greater than 0. Okay, so this is greater than 0, this the coupling constant between the proton and carbon. So when you are when you are taking a carbon spectra, now what you need to do, since this carbon is not connect means it does not affect the chemical environment of this carbon, and you forget about these protons, because the only this carbon is not affecting this carbon. Okay, but these protons can affect the chemical environment of this carbon, because this JCH is greater than 0. Now what you need to do for carbon spectra, you need the n value will be the protons which are attached to that carbon only. Means what you were doing for proton spectra, that is you were calculating the adjacent carbons number of protons. Then you are adding by 1. Okay. But for carbon spectra, if someone asks you and tell you that what is the splitting for this carbon, these protons, you need to calculate the number of protons to which this carbon is attached. Here, this is 3 protons it is attached to. So you will get 3 plus 1, that is 4. So for carbon also, this will be splitted into 4. Okay, because of these three different kinds of because of these 3 protons which are present. So for carbon, so you see, if off resonance, decoupling of one bond CH couplings are retained so that the signal for a particular C is given by the number of attached hydrogen in according to the n plus 1 rule. So for example, a CH3 shows a quadrate because for this carbon there are 3 protons attached. So n plus 1, that is 4. So quadrate. So don't get confused. This is for carbon spectra. What I have talked in the last slide, that is about proton spectra. So in carbon spectra, you need to calculate the number of protons attached to that carbon only, and then add by 1. You will get the number of splitting. For proton spectra, you need to see the number of protons which are present in its adjacent carbon. Then you add them and add by 1. You will get the number of splitting. Okay? I hope it is clear. It is clear, right? Okay, good. So this 13C nucleus is also about 400 times less sensitive as compared to proton. So these are the two reasons why they induce the carbon is not affecting the subsequent carbons peak. Okay, so that is being written here. Now if we are going to how many types of carbon, means in the carbon spectra, if you are looking, then if you want to find that how many types of carbon are present, then that is indicated by how many signals are there in this spectra. Means if you have 4 signals, just like the protons, I said that if you have 4 different signals, I am not considering the splitting here, the splittings are not shown. If you consider that how what are the different kinds of carbons, so on the different kinds of carbons you will have one peak, then you will have the splittings by the proton, that is there. But if the number of peaks will tell you, I am not counting the splittings, the number of gross peaks will tell you how many different types of carbon are present. What types of carbon? That is actually indicated by your chemical shift value. How? Because you know that carbonyl carbon have a particular ppm value. Then this CC double bond will have a particular ppm value. CC single bond, as I said, that these are more actually these are more shielded, so they will be present in the more shielded form and they will have a less ppm value. So the chemical shift will tell you that what type of carbon it is, and the number of signals will tell you that how many types of that carbon is present. Okay, and this intensity will tell you that how many type of the same carbon is present. So if there are 3 carbons which are of same, which are facing the same chemical environment, they will give a higher intensity as compared to a carbon which is only a single carbon facing a different chemical environment. Okay, so for this example, this is the acetophenone. You observe 6 types of carbon. How 6 types of carbon? This is one type. This is another type. Here you have another carbon. So 3 types. Then you have this benzene. So these two are identical. So 4. Then these two are identical. Meta positions are identical because no other functional groups are attached. So 5. And this one is a para position which have another carbon, that is 6 different types of carbons are present. And that's why you observe 6 different peaks. Now each of these peaks will be splitted by the amount of protons that are attached to it. Okay, so that all those discussion that we have done is about 1D NMR. Means either you are taking a pulse sequence which is corresponding to your proton, or it can be carbon 13. What if we can look into both these two spectra together? Or we in x-axis also you have a chemical shift value of proton, in y-axis also you means in x-axis also you have this chemical shift value of protons, and in y-axis also you should have another chemical shift value of proton. What if this is the case? Or what if you have two spectra, carbon 30 and proton. Okay, so now you have two dimensions. Here there was only a single line, only a single dimension. This proton is a single dimension, this carbon is also has a single dimension. But when you are looking into both of them together, that gives you a 2D spectrum. Whatever we have looked till now is 1D spectra. Now we are moving towards 2D spectra. Then you can ask me that why we require this 2D spectra? That answer you should have got by now. You cannot find the overall structure of your protein or forget about protein, the small molecules only from one spectra, because this all of these are attached by carbon as well as protons. You need information from both of them to actually get an idea how this structure looks like. For normal small molecules, I am telling you, not for proteins, because proteins are very large molecules. So for proteins, you need to go to more higher dimension, that is 3D NMR spectroscopy. So first let us understand 2D, then we will go to 3D. Okay, step by step. So as I said that there can be two different things that can be actually happening. That is, either both of the axes will contain the same nuclei, that is proton, or they can contain two different nuclei. One is proton, one is carbon. So if this is both of them are same, then they are known as homonuclear. Homonuclear because same types of nuclei are present. If you are looking into two different dimensions, one is proton, one is carbon, then it is known as heteronuclear. So 2D experiments can be of two types. Sorry, one can be homonuclear, another one can be heteronuclear experiments. Okay. Now, what are the different types of this homonuclear? One is this, for the homonuclear you can remember COSY, and heteronuclear you can remember HSQC. Okay, so the name is like this, correlation spectroscopy. Okay, and this is heteronuclear spin quantum correlation spectroscopy. So from its name only you can see that this is heteronuclear, this is homonuclear. Okay, and how these informations about, as I said, that how to got the information, how to actually make a structure, you need to have some information. One is how these carbon and hydrogens are attached through bonds, okay, as well as through space. Means if you have some carbon which is present here, as I said that the coupling constant can only give you up to 3 bond distance. But what if this proton is coming in space near to this proton? They are not connected by any bond, but their distance between them is very less, around less than 5 angstrom. Means this should look like this. This proton, because of the overall structure, they are coming near to one another. If you imagine, these are these two protons. This proton and this proton are not connected by 3 bond distance. But these protons can also affect the environment change. Means they can feel their environment if they are in space, they are apart by 5 angstrom. Okay, less than 5 angstrom. That is through space and through bond. Through bond we have talked about this coupling constant. Okay, the CC, and HH coupling constant. Another thing that is coming here is through space. How the means chemical environment is being affected through space. So that kind of experiment comes under this NOESY, which is this nuclear Overhauser effect spin spectroscopy. Okay, so we will be going through some of these 2D experiments and try to see what kind of information you get. So there are four different periods of a 2D experiments. One is your preparation, then evolution, mixing, and the detection. So as I said, there this T1 and T2. So there are two different means times you are using. Okay, delay times you are using, because you want to means as you remember, we need to first give a external magnetic field that should be always constant, and there will be a magnetic field which, or the radio frequency pulse, that is perpendicular to the external magnetic field. Okay, so we are actually preparing our samples for the 2D experiment. Then there is this evolution phase, which is because of the one of the T1. T1 means the relaxation along one axis, because there are two different spectra present. Then there will be mixing, and finally there will be detection, which will be this T2 value. Okay, so the 2D experiments can be divided into four different parts. Okay, now what is more interesting to know is that how you can actually get the idea of your structure from a 2D experiment. Okay, so first don't look into this spectra. You will be coming to into it later. First you think that this is, I am talking about a cozy. Cozy means in both of the field, means here also you have proton spectra, and here also you have proton spectra. So now try to imagine like this. You calculated the proton, you have performed a 1D NMR with proton. Okay, and you have got some peaks like this. Okay, for a molecule. Now these peaks have certain intensity. Now you actually, this is, I am showing you in a piece of paper. Now if you visualize, your eye is here, and you are visualizing these peaks from the top, you will see some dots, right? One dot for this, one dot for this, one dot for this, and there is another dot. The intensity, how much intense this is, this dot will be more bright. So for this spectra, you will get a more brighter dot, you will get a smaller brighter dot for this small spectra. So I'm looking into the spectra from the top. Okay, so now you will get some chemical shift values from for this axis. You take this similar information, you rotate this axis perpendicular, and draw some shifts again. These chemical shifts accordingly, means you what I am trying to say is that to create this 2D axis, first you take have the idea of 1D axis. You get some contours which is in respect to your this intensity and the splittings. Now you actually do this same phenomena in a y axis. So y axis also you have some splitting. Okay, and then you try to see that what is happening. You will be seeing that there will be some values, so there will be some peaks which are known as your diagonal peaks. Okay, so if you take these two in two dimensions, you will see two types of peaks. One is your diagonal peaks, which means that if you draw a diagonal, there will be some peaks which is falling in this diagonal, that is corresponding to this as well as corresponding to this. So this is your 1D H, and this is your 1D H. Okay, so in both of them this is corresponding, but you will also get some extra peaks which will not fall under this diagonal, which are known as cross peaks. These cross peaks will actually tell you whether the proton which is due to which you are getting this peak. So you are getting this peak, all these peaks which are present in this diagonal, this tells you how many different kinds of protons are present. Just like I said you how many NMR signals you will get, that will tell you how many different kinds of protons are present. This diagonal peaks represents that. Now, which proton is actually affecting which proton? Means just the way I said you that splitting will happen for these two protons. How you will get that idea? That idea is given by this cross peak. Means if this proton is in 3 bond distance with these protons, then you will get a cross peak which will connect these two dots like this. Means the groups, the functional groups which are present here, and these functional groups, they are actually connected with one another by 3 bond distance. So from this correlation spectroscopy, first you need to know what are the different kinds of protons that you have for this molecule through 1D spectra. Through 2D, you are actually looking into the connections. Because the example that we looked into, we had the structure previously and we were drawing that 1D NMR. So since we had that structure previously, we could have imagined and drawn that spectra. But mostly this is the reverse. You have an unknown structure, you get the spectra, and you need to go through the structure again. That can't be possible only by 1D NMR spectroscopy. Because you are not getting the information about the splitting there. You can get the information about the splitting by this 2D NMR spectroscopy. In COSY, these cross peaks, which those two dots are connected by cross peaks, which means these protons are connected to the protons here by 3 bond distance. Means you have actually got that there are 4 different splittings. Means here you have 3, here you have 4. So with respect to what, you have already got that how many protons are present in its subsequent carbon, because of by the 1D NMR concept that we just discussed. But now you don't know that how these carbons are connected to one another, or how these protons are connected to one another. That information is given by this cross peaks. That's why 2D NMR experiments is very important for determining the functional groups of this small molecule. Now let us take the example of this one. So this is a very simple molecule. It's not complex like this. I have taken the example of a very simple chemical molecule. So first what you need to do, you first forget 1 minute. You first forget this is present here. You forget this. Okay, I am deleting it. Okay, you just look into this molecule. What you do, you take a normal 1D proton spectra. You get this kind of peaks, right? You integrate these peaks and you get into some dots, just the way I showed you. So you integrate the peaks, means integrate means you integrate the intensities of these peaks and you get a contour like these dots. Okay, from these peaks, from the 1D NMR, what you came to know is that this proton, means whatever be this proton, you don't have the structure also. You don't have the structure. You have this molecule. So what I will do is that I am pasting it here. I am removing this. You have that molecule, some molecule. You have taken a proton spectra, 1D proton spectra, and you don't know the structure of the molecule. You need to find the structure of the molecule from this 1D spectra, then also a 2D spectra. Now what I did is that I have this 1D spectra. From here I know that the protons which are attached with the carbon here, these protons are more shielded. Okay, so this must maybe a methyl carbon, but we don't know. We know that the carbon which is present adjacent to the carbons which has these protons, they have actually 2 protons attached to it, because there you have 3 peaks and this is a proton NMR. So adjacent carbon have how many protons? Plus 1, you will have that splitting. So here you have 3 peaks. You know that the protons to which this carbon is attached, the subsequent or the adjacent carbon has 2 protons. That information you know. Now here you see a single peak, which means the adjacent carbons to this carbon does not have any proton, due to which the n value is 0. You are getting a single peak. 0 plus 1 is 1. For these protons, you know that the adjacent carbon have how many protons? 3 protons, right? Due to which you get 4 different peaks. So these information you can get from a 1D spectra, but you don't know that how the structure looks like. Means how this, whether this carbon is connected to this carbon, means these protons are connected to these protons, or these protons are in vicinity with these protons. You don't know that information. So for knowing that information, what you do, you take this 1D spectra like this, you keep it in one axis, you have these contours, again you put this in another axis. So as I said, you will get some diagonal peaks like this. If I draw a diagonal here, you will get some diagonal peaks, means, which means that there are, so this is falling in this line. Okay, so this diagonal peaks, as I said, this represent that how many different kinds of protons are present, that you have already seen. These 3 different types of protons are present, but how they are connected, so that information is given by this your cozy. So if you draw a line from here, and if you draw a line from here, so you now see that this peak, which was corresponding to this one, where we saw that the subsequent carbon to which it is attached, it has 3 protons. Okay, due to which it you get splitting. It is actually connected to something here. If you see this is your this peak. Okay, which have shown you that the carbon to which it is attached, it has 2 protons. That's why you got 3. From here you get an idea that this is a molecule like CH3 CH2. Okay, because this methyl group, the protons for methyl group, you have 2 plus 1 3 splittings, and for this one you have 4 splittings, and they are bonded with one another. So from here you get an idea that you have something like CH3 CH2 in your molecule. Okay, now you have, and you have this one, so there you get 2 cross peaks, so both of them is giving you the same information. But what is interesting is that this carbon, means the protons attached to this carbon, it seems that this is a methyl group, because there is a means this is something which is having a means single chemical environment, and there are no particular means molecules which are present adjacent to it. Means there are no subsequent, the adjacent carbons does not have any proton. This is that kind of molecule. Okay, so how it looks like, then it should be like C double bond O. Okay, and there can be one proton attached to here, and in the subsequent one, this one, there can be some functional group like O, which does not have any proton, due to which you get a single peak like this. Okay, and you also have this functional group CH3 CH2. Okay, so now if you now like try to look into the structure, if I copy paste the structure here, you see there is this oxygen which is separating this carbon from the other, this carbon has one proton, but in this this carbon does not have any proton. This one has some protons, this one has some protons. These two are methyl, and they are facing the same chemical environment, but this ideally they should face, but since this methyl group is attached to this carbonyl carbon, these methyl groups will not have subsequent carbon which has a proton, so this will be behaving like a different way, due to which you will get a single peak like this. Okay, so all these three protons have not been splitted because there is no proton present in the subsequent carbon. And I said you that there is something CH3 CH2 because you got a cross peak here. That is this CH3 CH2. So here the protons which are present here CH3, this will be splitted by the CH2 because this carbon has two protons. So the proton it will have this three splitting. Then again for this carbon you have 2 but the subsequent carbon has 3. So 3 plus 1 is 4. So from this 2D spectra you can actually tell that how this proton systems, this all proton systems are connected to one another. Okay, so this you did for proton proton. Now you can actually perform this experiment for carbon proton. Then you will also get the information about the carbon. Then you can actually draw the full the structure of the molecule. So you need to carry out different experiments for getting into this structure. So the practice that I showed you, this is only for showing you how this cozy looks like. Okay, now so I have very few means I have half an hour left. So, but this is all about the 2D spectra of solving small molecule chemical structure. But in biology, which we use for protein, how this NMR is utilized, that I have not talked yet. Okay, so in for proteins it is much more complex because proteins have thousands of these functional groups. Okay, and they have different side chains. So how you can actually look into the structure of the proteins, that is much more important. So we will be going forward with that. Okay, so let me do that. Then only I will discuss with you the week 6 assignment. So then you can actually week 6 assignment will be very easy for you because some questions also came from this part if you have solved. So if you see, so you imagine a biomolecule. For example, you have a protein. In that protein, you have mostly that protein is made up of alpha helix, and I have one protein which the protein is made up of mostly of beta sheet. Those who do NMR, they will just collect a 1D spectra and they can tell you that your protein has more alpha helices or they have more beta sheets because they have characteristic shifts, chemical shifts in the 1D proton spectra. If you just take the 1D proton spectra of your protein and do a COSY, or you can take a HSQC. Okay, you take a 1D proton spectra. So from the 1D proton spectra, you can't tell whether it is alpha helix or beta sheet, but you can tell whether your protein is properly folded or not from a 1D proton spectra. Because in a 1D proton spectra, if you see some peaks, the means in the negative ppm value, in the negative ppm value if you see some peaks, which means that those that protein is not properly folded or they have more unfolded regions. Okay, but now from the 1D spectra, if you go to 2D spectra, you will see that there is, if the peaks are concentrated in one region around 8 ppm value, then your protein has more alpha helical structure. But if your peaks, these contours are more spreaded in your 2D spectra, then it has more, means it has scattered peaks, then it is more of beta sheet. Beta sheets are present more. Okay, but if it is more disordered, then you will not see this spreaded spectra. You will see all your peaks will be clumping in one region, which means that your protein is disordered. Okay, and if it is a molten globule, it is similar that this disorderness and this molten globule, you see in molten globule you can see peaks which are clumping with one another. Okay, so by looking into the 2D spectra, you can tell whether your protein has more alpha helix, more beta shape, or more disorderedness in it. Okay, 2D proton spectra. Okay, sorry, 2D spectra of proton nitrogen. So this is known as the heteronuclear. This is known as HSQC, heteronuclear spin quantum number that I showed you previously. Now, for each of the amino acids, the protons you have in the side chain, they have a characteristic shift, side chain as well as the backbone. So in amino acid, if you remember, they have this C alpha carbon which has one proton, okay, and they have some side chains which have, for example, C alanine. If I see, so there is this alpha proton and the beta proton which is attached to the beta carbon, and here is your COOH, and this COOH and NH2 is present. Okay, this NH2 will also have some, these protons will also have some chemical shifts. And here I am showing you the chemical shift value of the alpha hydrogen and the beta hydrogen. And this backbone nitrogen values and the protons, if you do a 1D NMR, 2D NMR spectroscopy of HSQC, you will have this backbone nitrogen as well as this proton value, as well as the nitrogen protons which are present in your side chain. Okay, like this lysine you will have. So these are the different characteristic spectra. So we know that in which region alanine C alpha value will come, in which region the protons attached to the C beta will come for alanine. Similarly, we know it for all the amino acids. Okay, so similarly for the proton, we also know the 13C spectra of all the amino acid, where C alpha shift should come, where C beta shift should come, and all these gamma, epsilon, delta, all these values you can actually, there are tables, there are specific values which we know that if there this C this the shifts are shown in this region, then that the shifts corresponding to the amino acids we know, means that shift which we get, that is actually related to some amino acids, so that information we know. Okay, so this is what I said you, that means if you take just only a 1D NMR spectra, you will see some means there are certain regions which will show you some protons, like the tryptophan protons. The protons of the tryptophan are most deshielded because of this ring structure of the tryptophan. Okay, so you see the tryptophan indole group protons and the resonance, due to the resonance in the tryptophan side chain, you will have most deshielded protons of the tryptophan. Then you will have the backbone NH group. So this region will tell you the backbone NH group. Then comes the aromatic hydrogens, then the backbone hydrogens, C alpha hydrogens. Then you have side chain hydrogens. So all these are actually assigned, and you also have water. So in NMR spectra, what we do, we always dissolve our protein with D2O. There is this we where we want that the contribution of the water should be actually null, because water also have protons, and that protons can get exchanged with your proteins, due to which you always use a solvent like D2O in the means in this kind of experiments, okay, where you don't want your proton to get exchanged with the surrounding. So there is also a peak of water, a large peak of water here. Okay, now, as I said about that, there are different spin systems. Spin systems means that these all have the chemical shifts of these are related to these by some distance, like this J coupling values, just like we saw for carbon-carbon single bond in the case of three bonds should be there. In case of 1D NMR for small molecules, there are certain spin systems of the amino acids. So these spin systems, if they are connected by three bonds, then they can affect the environment of one another. Okay, so that is the concept of spin system which is coming for the proteins, and that spin systems are very important to solve the structure of a protein. Okay, so this one, how to solve a structure, we I will be telling you. Just let me first discuss with you about the assignments. Then I shall tell you the further how to get into your structure. Uh, so first, let me discuss with you the week 6 assignment, and then I shall tell you the 2D and 3D NMR experiments of your proteins. Okay, means we will look for the instead of the small molecules. The practice that we did, we actually looked the cozy for a small molecule. We will look for a small peptide, how the cozy HSQC looks like. Okay, so that we will be doing. But first, let us discuss the question. So the first question was, which of the following electromagnetic radiation is of lowest energy? 1 minute. So while discussing about the NMR spectroscopy in the last um, session, in the last Friday, I said you that in NMR we use a radio frequency wave, but in X-ray we used to use this X-rays. But in NMR we use this radio frequency pulse, right? When I said you that the perpendicular magnetic field, there will be a radio frequency pulse. So why radio frequency we use? I said you that the two spin states that I was explaining you, that there are two spin states for this proton. The difference between this energy of these protons and all those nuclei that are NMR active, they are, the energy is very less. This del E value is very less because I said you that there is a very less amount of population difference between these two states, which makes them this del E value to be very less. So I said you that we use radio waves because these radio waves have a lowest energy. Means when you have compared with the wavelength and the energy, radio waves have the, in the, if you look into the electromagnetic spectrum, radio waves have the highest wavelength. So those which has the highest wavelength will have a lower energy. Because of this, E equals to h nu and E equals to h c by lambda. So energy and wavelength are inversely proportional. Okay, so that's why the answer to this question will be radio waves. So from here, you can, I have just discussed with you last class that with, if you have actually watched my video, then you could have easily given the answer. Okay, MRI is based on which of the following techniques? So in the last session when I was discussing NMR, I said you that a technique which is very means similar to NMR in our day-to-day life is this MRI. So in MRI also you have, if you remember that for doing MRI, so people, the pathologist or the laboratory in which you are going and they are testing your means testing you through MRI, they will tell you that you should be hydrated. So you should drink water and you should be hydrated when while taking, means you should not be hydrated. Sorry, you should not be hydrated. You should have a proper, because if you take water, so that's just like I said you that this water had NMR active, so that water will actually hamper with your means this NMR spectra. Just like we talked about the proteins, that if you saw dissolve a protein in the water and do NMR spectra, this water's protons will also give a signal. Okay. So in MRI, people are being asked that you should not drink that much water because already in your body, in your blood, you have water. You don't want some water in your tract or something which can actually affect the overall idea of NMR. So NMR and MRI have a similar procedure. In MRI also, all the protons which are present in your body, they will be directed towards an external magnetic field, that is this B naught, and all these protons will be aligned to that external magnetic field, due to which you can get the information out of the MRI. Okay, so that is similar to your NMR spectroscopy. So the answer to this question is B, that is NMR spectroscopy. Then low frequency waves will have. So just we discussed for the first question. So the what these low frequency waves will have? Low frequency waves from the Planck's constant, if you see, E is equals to h nu, which means E equals to hc by lambda. Energy is inversely proportional to the wavelength. Okay, and energy is directly proportional to the frequency. So it has said that low frequency waves will have. So low frequency means low energy. Shorter wavelength is not satisfying it, because low frequency waves will have a higher wavelength, because frequency and wavelength are inversely proportional. Low frequency wave have a long wavelength. It is correct. Low frequency wave does not have a high energy, because this frequency and energy are directly proportional. So if it is a low frequency wave, it will be a low energy wave. So the answer to your question is third question is this B, that is long wavelength, right? So this is the answer. So whenever you have find any difficulty, just stop me and ask me. Which of the following is NMR inactive element? Which of the following of them are NMR inactive? So how you can actually know that? I shared you this table, and I said you there should be an odd atomic number or odd mass number, or both of them should be odd. Then only it can be NMR active. Now carbon 12 is not. It has a even atomic number. Now here proton is okay. So H1 is okay. Then N15 again it is odd. C13 again the atomic number is odd. Only carbon 12 has an even atomic number, which means the NMR inactive element is this carbon 12. So the answer to the question is A. Which one of the following is not a factor affecting the chemical shift in NMR? So which one of the following is not a factor affecting the chemical shift in animal? So I said you that how this effect is means chemical shifts are being affected. Once I am telling you repeatedly resonance, inductive effect, and all this hybridization is also responsible for shifting of these electron clouds. But I have nowhere talked about the absence of chiral carbon. So there may be a chiral carbon or there may not be a chiral carbon. This does not actually affect, means absence of a chiral carbon does not affect the chemical shift in the NMR. Okay, so the chemical shift is affected by these three forces: hybridization, inductive effect, resonance. So the answer to this question is option C. Then, then next five questions. Which of the following solvents cannot be used in NMR spectroscopy? So we have just discussed, but I am telling you again. So this D, that is this deuterium, this has a net spin value of 0. The oxygen also have a net spin value of 0. Why deuterium has net spin value 0? Because it is two atomic number of this will be 2, right? That just like the protons, you have this you have a odd means atomic number and mass number. If for proton it is 1 1, but it is 2 1 for the deuterium, right? So for that you have a magnetic or the spin value where will be 0, and this deuterium will be NMR inactive. So that's why if you use D2O, it will not affect the, it will not add noise to your signals. But if you have water, these protons are NMR active. So this can actually give noise to your signal. So that's why the water is not a favorable solvent to use. Okay. The answer to this question is A. Why C13 coupling is not observed in NMR spectroscopy? So as I said, this slide actually tells you that I said you that in the carbon 13 has a lower abundancy. That is correct. The A option is correct. C2 is C12 is NMR inactive. So we discussed why it is inactive. So it does not contribute to any NMR signal. C13 has 400 times. So here I was discussing C13 has 400 times weak signal than that of hydrogen. So these all three are correct. So that's why the answer will be all of these. So the answer is D. In C13 NMR, the carbonyl carbon will give signal in the range of. So carbonyl carbon, I said you that carbonyl carbons are more de-shielded. So that will be above 150 ppm, it will give a signal. So the answer to this, if you see this slide, I have given this carbonyl carbons above 150. So the answer to this question is C, option C. Which of the following is a space correlation NMR method? So which of these following is a uh, space correlation NMR method? So if you see, so now means for going into it, I can actually for solving last two questions, I can first actually tell you little bit about these 2D experiments for the amino acids. Then it will be clear to you. Okay. If you have any question, you can ask me. Okay. So, so we were here, right? So 2D NMR spectroscopy for the amino acids. So I said you that for each amino acid we have a chemical shift values that we know. That if a peak is coming in this region, so we know that is alanine. So we know for isolation there will be two distinct C alpha, C beta protons. Okay. So all of them and all of their backbone nitrogen values we also know. Okay. Now, what we need to do is that first we need to identify resonances, spin systems, chemical shifts for each amino acid using COSY and TOXI data. Normally, for if you want to see how a structure looks like for a peptide, it can happen. For a large protein, the 2D NMR spectra will not be sufficient. You need to go for 3D. But for a peptide like this, alanine, isoleucine, leucine, nitrogen, glycine, tyrosine. So this is a kind of peptide. So to solve how these peptides means how these amino acids are connected in this peptide, you need to do two things. First, you need to actually identify the spin systems, just like I showed you here. Spin systems with the help of this COSY and TOXI. TOXI means total correlation spectroscopy. So here you for COSY you used to get only one diagonal peak. If for TOXI you will get the protons which is being seen by all the protons in this means all the diagonal peaks will come. There is a total correlation spectroscopy. So that's why all the peaks, diagonal peaks will come in TOXI. So you need to first identify your spin system through the COSY or TOXI data. Then you actually use this NOSI. NOSI tells you how the spin groups are connected to one another in space. Through that, you can actually get your peptide example. Okay. For example, now let us identify the spin systems with the help of COSY. So for alanine, if you see there are three kinds of protons. One is your means one is your proton of the nitrogen backbone proton. One is the proton attached to your C alpha and the protons which is attached to the C beta. So they since there are three kind of protons, you will get three different spots in the diagonal, just like we discussed for small molecules. Now, how they are connected to one another. So in Toxi, as I said, you get the shift, the peak for this proton as well. Okay, so these give a total correlation. So you actually from this you actually see that these three, this all is a single amino acid. This is a single spin system because these are connected by diagonal peaks. Okay, so means these are all separated by 3 bond distance and they are falling under one amino acid. And how these are connected with one another, that is been given by this diagonal peaks. For leucine also you calculate one. Now, these cozy protons that are directly that I just mentioned, and toxi means connects all protons that share J coupling partners, spin systems. So in toxi, you will get all these protons cross peaks. But in cozy, it is only 2 to 3 bonds distance cross peaks you will get. Okay. So you actually first do this cozy and toxi for each and every amino acid, and you identify the spin systems. Now you need to align the spin systems with one another. Now you see that two cozy spin systems, they are connected by this nosy. Nosy means that this proton which is not connected with the next proton by 3 bond distance. Here you connect 1, 2, 3, 4, 5. But this proton can actually see this proton or affect the chemical environment of this proton. So for that you will get another cross peak. So if you imagine, so these are, there were two, these were, this is one spin system, this was another spin system, and for each of this is another, this is one spin system, this is another spin system. Now you see that there will be certain peaks, these green peaks, in the, when you overlap the two spin system, there will be some extra peaks which will tell you that the protons of the alanine is connected to leucine or not. If they are not connected, you will not get this extra green spots. So that is your nosy. So now if you have these extra spots, now you know that alanine and your leucine are connected with one another. In the same way, you do for all the amino acid, and you will be looking into the structure of a peptide. Okay. So this is the 2D NMR peaks of amino acid, how it looks like. Okay, so for means all the means where I have shown you that in which regions the means chemical shift values for these amino acids you can find from a 2D HSQC. This is the heteronuclear spin quantum number experiment. So what we have done here is the total. This is the homonuclear one, and this is the heteronuclear. From heteronuclear, you can directly tell that in which region which peak is corresponding to which amino acid, because you will have one N, another one proton. So you will get the backbone NH values here. Okay, and also some protons and nitrogen values of your side chains like this lysine. So that you can also get. Otherwise, you will get these backbone values here, and you can actually get your this toxi-peaks, this hydrogen A, B, C, all these you can actually, these values, we, as I said, we know the table, we know. So from here you can actually assign which peak correspond to which amino acid. Now for, but 2D is not sufficient. So for 2D, you can, for proteins, you need to do 3D experiment for solving the structure of the proteins. So you need to add another dimension, that is here carbon 13. So you imagine this nitrogen proton plane, and you travel this plane across a carbon 13 axis, and it will look like a cube, right? So if you do a slice of this cube, you will get a 2D NMR spectra. So many 2D NMR spectra are connected to one another in one direction by a 3D, by a 13C carbon. And then there are, you are getting three different, means there are different kinds of 3D NMR experiments like HNCO, HNCACO, CBCACONH, HNCACB. Okay, so what this spectra, what information you get into, if you perform an HNCO experiment, means how these experiments are designed by differing the pulse sequences, radio frequency pulse sequences that I discussed in the first part of today's class. So if you do a HNCO, you will see the carbonyl carbon and the nitrogen proton which is attached just adjacent to it, means I minus 1 carbon and the ith proton. So in this HNCACO, you will get this one as well as the I plus, means I plus 1 carbonyl carbon. So these two experiments are complementary. If you perform these two experiments, you will get information which can give you the idea of the structure of the protein. Again, you can do two complementaries like CBCSUNH. Here you get the information about the C beta. C beta of the I minus 1 for this CBCSUNH, and if you do HNCACB, it will give you the I minus 1 C beta with respect to the own C beta, C alpha C beta. So from these complementary experiments, you can actually go to the three-dimensional structure. Start with, means these are some suggestions. I will share this slide with you. So in future, if you do some NMR spectra assignments, you can follow this. Glycine have only one C alpha because they do not have any C beta. So you will see only one peak for glycine when you do an HSQC. Okay. Alanine has a C beta which is upfield. So this C beta of alanine is around 18 ppm. So for alanine, you can just see the C beta proton and you can see that this is alanine. For threonine serine, the C beta, the means what I am telling you here is this table, C alpha, C beta. So for serine, the C beta values are in negative. The alpha values are positive, C beta are downfield. So for that so serine and threonine can be easily identified by the C alpha, C beta. Then you can actually uh, carry out these 3D experiments to actually find out the connection between two spin systems and try to find out the structure of your protein. So in a summary, so these tables can actually help you to know what experiment give you what result. COSI helps you to see the means proton-proton relation when they are separated by 3 bond distance. TOXI gives you the whole scenario, means this protons is connected to which all the spin system there will you will get a means diagonal peak. Nosy is through space. As I said, if it is less than 4.5 angstrom, then this proton's chemical environment can affect these protons. Rosy is similar to nosy, but rosy has means this is more known for small molecules, and this is much easier to acquire from nosy. Okay, and this in rosy also you actually get this splitting through space. Inadequate means this is for carbon. So how this carbon is affecting another carbon, that is actually given, means C13 that is actually given by inadequate. Then there are these are homonuclear. Then there are heteronuclear experiments. So what HMQC does, what HMBC does, HMBC does that here this proton is not associated with the subsequent 3 bond distance. So it is going to a further three carbon which is one carbon away from it. Means this carbon 1, 2, 3. So 3JCH 1, 2, 3. So this carbon this proton can be affected by this carbon 1, 2, 3. Okay, CH. So I said you that one bond CH for the 1D experiment. But this HMBC 2D experiment, it can see the proton which is connected to this carbon in 3 bond distance. Just like what we see for HSQC, that was means for the protons in 3 bond distance, this is JCH3. Then there are different experiments. So these I have given you so that you can actually just look into this table whenever you forget and get an idea about what experiment is about what. Okay. Now if we go to this ninth question and 10th question, we will be able to solve. So here it is telling which of the following is a space correlation in our method. So we learnt either rosy or nosy. These two are space correlation. Through space it can affect the protons, the chemical environment of the protons. So that is given by this rosy. Rosy from the name, it's a rotating frame overhauls effect spectroscopy. It has been known as also camel spin, cross relaxation appropriate for mini molecules emulated by log spins. So this is through space. Others are not through space, they are through bonds. So the answer to the question will be C. This is the answer is rosy. In which of the following methods direct one bond correlations are suppressed? If you see HSQC have direct one bond correlation. Rosy, that is through actually space. Okay, so rosy has the different concept. Okay, inadequate inadequate also you have some means if you have looked into that a homonuclear, there was one distance, but direct one bond is suppressed here as HMBC. So HNBC you have three bonds to travel. Okay, direct one bond correlations are suppressed in the HMBC. That's why the answer will be B, that is HMBC. Okay, so this is all about the NMR part, what I wanted to discuss with you. From next class, we will be dealing with the spectroscopy and the spectroscopic techniques. Okay, so if you guys have any doubt, you can tell me. Means right? It has a this is only a 2 hour class, and I have tried to give you some concepts, but if you want them in depth, please look into such videos. He have elaborately explained them, and if you get any doubt, you can ask me. Okay, any doubts? Uh, any doubts you have? You are able to get the idea, right, Shani? Okay, okay, okay. So if you look into such lectures as well, if you get any doubt, you can just ask me in the next session. Okay, okay then. Bye, bye.